A function is constant if it has a slope of 0 on that certain interval of x values. So like it's constant because it stays the same. It's a horizontal line. A function is increasing on an interval if it has a positive slope. So looking from left to right, if it's going upwards on that interval, it is increasing. And it's decreasing if it has a negative slope on that interval, going downwards as you look at it from left to right.
Let's look at both of these, starting with the domain and range. So on the one on the left here, my domain, if you look at it from left to right, it goes from negative infinity, and then one piece of it stops at the x value of 2, but the other one picks up there and has a closed circle, so it doesn't skip any x values. It goes from negative infinity to infinity. For its range, the lowest y value that it reaches is at negative 1, and then my line's going upwards, hitting the y values larger than that. Actually, it has an open circle at negative 1, so my range is going to be parentheses negative 1 to infinity. And there are two pieces, but they both sort of overlap. The first one would continue up and include the second one. For my function on the right, my x values go from negative 5 with a closed circle included point to positive 5. My range, I realized I didn't actually give you a scale on your y-axis, so let me give you some coordinates. Let's say those points are 5, negative 4, and 5, 4, which means my range goes from negative 4 to positive 4. Now talking about our new stuff, the intervals where my function is increasing are where it has a positive slope. So on the left, that piece right there. And then my other function has two sections or two intervals where it's increasing and has a positive slope. When you're writing this, you're always using the x values to describe the intervals of increase, decrease, or where it's constant, not the y's. So we're saying it's increasing for this set of x values. So from 2 to infinity, and those are actually always parentheses because it's not really increasing at your endpoints. For my other function, it's increasing on the left between the x values of negative 5 and 2, and then also, so union, the x values of 4 to 5. And then if we're looking at where it's decreasing at, that's where it has a negative slope looking from, again, left to right. So don't look at the direction of the arrow. Read your graph from left to right. Think about where are its y values decreasing. So this one's decreasing from negative infinity up to the x value of 2, and my other one's decreasing between the x values of negative 2 and positive 2. And then constant, my function on the right hand side has a section where it's unchanging y values horizontal between the x coordinates of 2 and 4. My one on the left is never constant. A function is what's called continuous over an interval. Again, we're describing the x values where this happens. If you can trace the graph on that interval without having to lift your pencil from the paper or the screen. If you have to lift up that pencil to jump over something, a hole, an asymptote, then you have a discontinuity at that value. Let's look at a couple of functions here. First off, we're going to state where they have discontinuities. So for g of x, I could kind of trace it, but then when I get to the point right there with my x value of 1, it's a hole. I have to lift up my finger to stop tracing it there. That is a discontinuity. So there's a discontinuity there at the x value of 1, or since it's at a specific point that you know the y value of, you could also say there's a discontinuity at the point 1, 3. If you look at your other function f of x, well, it's continuous, going, and then I kind of have to jump over to get to the other half of my function, and then I can start redrawing. That one has an asymptote. It's got a discontinuity for the x value of 2. So I'm just going to say there's discontinuity at x equals 2. Specifically, there are different kinds of asymptote, or different types of discontinuities, and that one's an asymptote. Now, the intervals where my function is continuous is basically everywhere else that there's not a discontinuity. So g of x is continuous for the x values of negative infinity to 1, skip over 1 because I have a discontinuity there, and then from 1 to infinity. And then my f of x is continuous everywhere except 2, so negative infinity to 2, union 2 to infinity. You could have multiple discontinuities on a function as well. So let's think about symmetry for a second. There are a couple of types of symmetries that we're going to discuss for functions. Even functions are functions that are symmetric with respect to the y-axis. So like an absolute value, you could fold it across the y-axis and it would match up with itself. Odd functions are symmetric with respect to the origin, which means basically you can rotate it 180 degrees, flip it upside down, and it's going to look the same as your original one. So say that I've got that function right there. I'm going to do a quick little copy here, and then if I take and paste it and rotate it, my drawing wasn't perfect, but it looks the same as before. That means it's odd. So let's look at each one of these here and decide whether they are even, odd, or neither one. I actually encourage you to pause this for a second and see if you can classify them before I tell you what they are, because I think you can get it from the definition I just described. Okay, well, the first one should be odd because it is symmetric about the origin. You could rotate it 180 degrees and it's going to match up with your original function. Yep. If you look at the one in the middle, it is actually neither even nor odd because although it does have some symmetry, it's symmetric to the line x equals 2. It's not symmetric to the y-axis, and if you rotate it 180 degrees, well, it's upside down. If you look at the last one, it is going to be even because it is symmetric to the y-axis. You can think about folding it across the y-axis, and it is going to match up with itself. So we've looked at a fair amount of function types in this class and Algebra 2. You're going to answer some questions about properties of these function types. So they are in your notes, but it is handy if you kind of know the general shapes of them. I'm going to run through and describe a few properties. I also didn't have arrows on these, so assume that they continue on. Okay, absolute value. You guys know this one. Looks like a V shape, symmetric. Natural logarithm, they have vertical asymptotes. Identity function is your parent function for your linear function, just named a little bit differently, just y equals x. Cube root makes a little bendy sort of S shape. It continues forever in both directions. Reciprocal function has an asymptote at x equals 0 in the middle there. Squaring function, also just your quadratic function. Another name for it is squaring function. Exponential functions are the inverse of logarithms. They have horizontal asymptotes, so along the x-axis there, instead of the y-axis like your logarithmic. Cubing function instead of cube root means you're taking things to the third power, so it grows a lot faster. Greatest integer function is crazy looking. You've probably never seen it before, but it's got some fancy notation, makes a lot of steps. You can kind of think of it as like a round down function. So like if you do 1.99 in your greatest integer function, you'll get 1. If you do 1.5 in your greatest integer function, you'll get 1. If you do like 2.1, you'll get 2. So it's the biggest whole number smaller than whatever you're plugging it in. Square root only goes in one direction because you can't do square roots of negative numbers and get real values.